So good morning. My name is Mary Striegel. All of you have probably met me at some point today because I was working on the registration desk. I'll be chairing the session this morning through to lunch. As I tell people that I'm very strict on time, we have a lot of papers to go through, and I think that there's a lot of information for you to enjoy and digest today. Our first speaker this morning is Dante Abate. Dante is a research fellow at the ENEA Research Center of Bologna, Italy. He has a degree with honor in humanities and a specialization in the protection and valorization of historical artistic heritage. His main research interests are related to 3D surveying and modeling, virtual reality, and visualization in the field of cultural heritage. He has a good familiarity with preparation with laser scanning instruments and software, as well as image-based modeling methodology. And I'll turn it over to Dante. Thank you.
I should find my PowerPoint first. Can you help me to find my PowerPoint, actually?
You want to advance? You can just hit that right there. Oh,
This is
it's
not
not
my
your PowerPoint.
PowerPoint. Yeah.
Pad's not working.
Go on.
Yep.
Good morning. I'll try to speak my very best English, but I'm still a little bit confused for 9 hours time shift from Italy to here. So I hope you have mercy for me. So I work for the NEA Research Center. NEA is a public non-profit institution in Italy, and particularly I belong to the technical unit of informatics and ICT. So the project I'm presenting today is about the 3D modeling of a gravestone, exploiting low-cost range and image-based techniques. So this is a brief summary of my presentation. First, I'll show you the initial aim of the projects and the results. So then I go through the problems emerged during the model analysis, and then it came up a new project parallel to the first one, and then the new result and final conclusion. So we have been asked to make the 3D models of this gravestone. This gravestone is placed in the Medieval Museum of the city of Bologna, and among the collection of gravestones, this is the most important since it still preserves many areas with the original color. So the museums who want to make an exhibition with 3D models of this gravestone performing virtual restoration. It was made during the first half of the 14th century, and it was supposed to adorn the tomb of Bonifacio Galluzzi. Bonifacio Galluzzi, which is the main character of the gravestone. So the final goals were the virtual restoration of the gravestone and, of course, the documentation of this object. So since it was a not funded project, so we have to deal with short amount of money, we just used what we have in the lab at that moment. It means that we use a triangulation laser scanning, and in particular this model, which is a low-cost device, costs something like $2,000. The next engine 3 desktop scanner has is a box and has a field of view of 30 centimeters for 20 centimeters. So it means that you had to acquire many range maps in order to model an object. And I think it was born to model small object instead of big one. So we started the survey, acquiring range maps starting from the bottom left of the gravestone and moving to the right side. And in a bootstraphic path, we acquired something like 100 range maps. So as I said, it was in particular 95 range maps, and for each range maps it took something like 5 minutes of scan process. It means that the scan process, then the computer has to compute the acquisition. You have to move the scanner, make the new scan, and so on. So for each scan, it takes something like 5 minutes. So the museum was open for us only on Monday afternoon. I mean, the museum was closed to the public, but the office was open. So we could stay there only from 2 p.m. to 6 p.m. because if you stay in the museum and you have people going around and maybe you have to put wires around, they can fall on the ground and it could be dangerous. So that object is something like 4 meters, well, maybe 3 meters long and 1.5 high. But we took something like 4 days of surveys. It means it was 4 weeks of survey, so 1 Monday per week, which is a lot of time to model such an object. Plus, you have to add the post-processing step, which is something like 4 days, 5 days working in the lab, in the office. For the post-process, we used the MeshLab software. MeshLab is developed by the ISTI lab of the Italian National Research Council. First of all, we filter each range map. Then we go through the alignment process, which MeshLab is a semi-automatic alignment. It means that in the first step, you have to click on at least 4 homologous points for each range map, and then you can run the ICP algorithm to make the final alignment. At the end of the alignment process, we run the Poisson surface reconstruction algorithm in order to have a closed model without any holes. The final models consist of 15 million of polygons. So here we have some screenshots of the final model. This is the entire model, and here we have some details. This is the main character, character of the gravestone. Here we have other details. This is one of the students on the left side, and this is the 3 students on the right side. So at the end, we were sort of satisfied from the acquisition and the modeling, but then we realized that we had some problem. So we went through the model analysis. I put these slides after the keynote presentation of yesterday because they say that they made a lot of analysis on these frescoes in Florence, and at the end they end up with no results. Okay, we end up with some results, but there were errors about it. So if you see the model, it ended up that we had a lot of distortion along the main axis. Here we have some slides that show you the distortion of the model. So we spend a lot of time modeling this object for weeks, 4 days in 4 weeks of survey, plus the post-process in the office, and we end up with a model that's what's wrong. So we tried to figure out how to save time and have a result that looks better than this with the almost same accuracy. So the distortion was due to the missing overlapping area of the single range map. So in order to, if you, for an ideal alignment, you need something like 50–60% of overlapping area among two range map. But to speed up the process, since we hadn't much time, we decided to reduce this overlapping area between each range map. But this missing in the overlapping area result in the distortion among all the model, which cannot be corrected afterwards. So we decided to, in order not to make the same mistake the next time, to check if we could use other different techniques to model such an object and give such result. We decided to check some computer vision software. As you may know, computer vision techniques makes 3D models from 2D image. Comparing with photogrammetry is an automatic process. It means that you give the software the image, click the button, and wait almost for the result. But at the end, you have the 3D model, but it doesn't any metric result. It means that you have afterward you have to scale the model using ground contour points or known measure. We tested this software, so the Agisoft Photoscan, which is a commercial software produced by a Russian software house. 123D Catch produced by Autodesk, Visual Structure for Motion, and Apero MicMac, which is a software developed by a French research institute. Here you have some details. So the output for 123D Catch, which is a client-server software, is a mesh as like Photoscan, whereas with Visual SFM and Apero, you get back a point cloud. The computing time was, for the first three, was almost the same, whereas with Photoscan, it was much longer. We used this software on a workstation with 16 cores and 24 gigabytes of RAM. The user interface, just Apero MicMac can install only on Linux operating system, and you have to perform all the command through the command line. So you have some details about the use of cross section with laser scanner and 123D Catch, and the vector exaggeration means bigger is the vector and larger is the error. Here you have the first section and the second one. This is the section with the Agisoft, and basically you have the biggest error is on the top of the section where you don't take photo from that angle. Basically, we just moved in front of the gravestone and taking picture, and we didn't go up to take a picture from that angle. And here you have the same thing, and photos can show that there is really, really big overlapping between the two sections. The next two are the models that you obtain triangulating the point clouds, and they show pretty much big errors. This is the first one. This is the second one. Well, the error on the top part and the lower part. And this one is the last one with Apero. So the conclusion. Apero showed the most important divergence compared with the laser scanner. Okay, but we just performed some basics filters among the point cloud before the triangulation. So maybe improving the post-processing on the point cloud and then the post-process of over the triangulated mesh, maybe you can get a better result. Photoscan showed the best result comparing with the laser scanner models. And so the next time we are going to make a project like this, we'll evaluate better the technique we are going to use according to the final code of the project. It doesn't mean if you have the scanner, you have to use it no matter what. You can use some other technique which maybe is cheaper and faster. You can get almost same results. And I mean, this project show us that you can get with image-based technique, which, as I said, are cheap, much more cheaper and quicker. You can get better result in terms of cost, accuracy of the model, and working time. So, thank you.